Okay, greetings. Here we are again. We're tackling another MIT Integration B problem. So let's go ahead and have at it.
Specialized in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your saction, vocal toe-to-toe, impeccable, splitting your back, son, simple as addition and subtraction, black thought, the infinite relaxed one.
Before we get started, you may say, what's the fascination or the obsession with all these MIT Integration B problems? I like doing MIT Integration B problems for a couple of reasons. One, they're pretty interesting problems for the most part. They're non-conventional. Generally, they bring some type of novelty or some type of interesting nuance to the problem. And additionally, they're problems that the introductory calculus student can do. So the student in Cal 1 or Cal 2 or AP Calculus has been taught the tools to be able to do these problems. I mean, basically you're doing u-sub or you're doing integration by parts or you're doing some type of algebraic or trigonometric manipulation. So you don't have to be in Cal 3 or differential equations or or real analysis to be able to do these problems. So that's why they're very good problems. They're interesting for the most part, slightly difficult, I guess you can say, but they're also at the level of where, the introductory calculus student can do them. And they're just so appetizing, like who can resist? So let's look at the integral that we have for today. So we're integrating e to the power of arc cosine x, right? So here, let's use our tool of choice, which would be u-sub. And if you look, I mean, if I'm going to do u-sub, obviously I'm going to make u equal the arc cosine of x. Okay, so once we do u, we do du. And so du would be -1 over the square root of 1 minus x squared dx. All right. And so typically in these problems, the du part becomes the pivotal part because, you're trying to make stuff match. And, all I have here is a dx. I don't have a bunch of stuff in dx. I just have a dx. So trying to make this match becomes the challenge. And so we try to see what we can do. Well, if I just want it to be dx, and then I can just multiply both sides by negative square root of 1 minus x squared. Okay, let's do that. See what happens. So this would be -1, the square root of 1 minus x squared du equals dx. Okay, cool. So now we have a match. We have dx and it equals this. Of course, the problem is this is du and this is x. We would like this to be du and u, not du and x. Well, we have a relationship between x and u, correct? Where u is the arc cosine of x. And if u is the arc cosine of x, that means that x is cosine u. And if x is cosine u, that means this is the negative square root of 1 minus cosine squared u. And 1 minus cosine squared u is sine squared u. And the square root of sine squared u is, of course, sine u. So then this is going to become negative sine u du. And that equals dx. All right, so now we're in a position to, do our substitution and figure out a mechanism for solving this guy. So let's do such. Let's get a brand new sheet. And let me just write let me write the substitution. So again, I'm integrating my u. U is arc cosine x, so I'm going to be integrating e to the u, right? All right, I'm integrating e to the u, and my dx is negative sine u du. So negative sine u du. All right, I hate when I do that. Let me just write this again. So integral of negative e to the u sine u du. All right. So that was great substitution. So now we got to figure out a way to solve this guy. This, if you know, if you've been exposed to integration by parts, you've probably seen something similar to this. So this can be done by integration by parts. It's going to take 2 steps. However, the issue with this problem, just a little background, but what you're going to make, normally it's u and dv. Since I have a u here, I'm going to say w and dv. Whether I make w e to the u or sine u, if I differentiate it, it's not really going to change. I differentiate e to the u infinitely many times. It's just going to keep being e to the u. I differentiate, and if I integrate e to the u infinitely many times, I'm just going to get e to the u. And if I differentiate or integrate sine u, it's just going to become plus or minus cosine u, depending if I'm differentiating or integrating. And then it's going to keep going back between plus or minus cosine or plus or minus sine. Again, depending where I'm integrating or differentiating will determine the sign being positive or negative. So basically, nothing really breaks down in it. It's not like a polynomial that eventually will become a constant or anything like that through differentiation. So, which one you make w, which one you make dv, it's up for grabs. And so what I'm going to do is I'm going to make w equal e to the u, which means dw is e to the u du, and I'm going to make dv equal sine u du, which means v is going to be negative cosine u. All right, now something to bear in mind. What I'm doing right now is I'm finding the integral of e to the u sine u du. That's what this represents. I am not finding the integral of negative e to the u sine u du. There's a pretty big distinction there. So what I'll do is, I'll find the integral of e to the u sine u du, and then I'll just multiply it by -1. But what I'm actually doing right now is the positive integral. I must state that distinction. So what I have here is the integral of e to the u sine u du is going to equal w times v negative e to the u cosine u minus the integral of v dw. So the integral of v will be negative cosine, so that's going to be positive. And you have an e to the u du for your dw, so positive e to the u cosine u du. All right. So now we have to find the integral of e to the u cosine u. Integration by parts again, in very similar fashion. So I guess I can write here before I go to a new sheet. So no, I think I'd rather do this on the new sheet. So I'm now trying to get, I'm now trying to get this guy. So I will write this on this sheet. I'm going to make w, and I'm going to use w again, equal e to the u, and I'm going to make dv equal cosine u du. So that's my method of attack there. So again, w is e to the u, which means dw is e to the u du. dv is cosine u du, which means v is sine u. All right. So let's write what we have. So just give you a reminder what we have thus far. So the integral of e to the u sine u du is negative e to the u cosine u plus, and now I'm going to do my integration by parts. So plus e to the u sine u, e to the u sine u minus the integral of sine u, well, e to the u sine u du. e to the u sine u du. And now you might say, well, here again, we have this insurmountable integral, right? And you will say, okay, so what you're going to do, just make w equal e to the u again and dv equal sine u du and just keep on doing this forever. Well, the thing is, the integral of e to the u sine u is what I'm trying to solve for. So there's no need to integrate further because I can just isolate this. So I can add an integral of e to the u sine u du to both sides. And what I'll get is I'll have 2 times the integral of e to the u sine u du equals e to the u cosine u plus e to the u sine u. And then let's say plus some constant. So now it's devoid of the integral. And so now it's pretty much solved. I need to divide by 2. And remember, I really want to find the negative integral of this. So I'm going to divide by -2. And therefore, the negative integral of e to the u sine u du equals e to the u cosine u plus e to the u sine u plus c divided by -2. And I could have put the plus c outside of the fraction if I wanted. It's no big deal. So we have solved the problem. We do want to rewrite it back in terms of x. It's now in terms of u. And so please remember, let me go back to one of my earlier sheets. So please remember that u is the arc cosine of x. So let's go ahead and substitute this back in terms of x. I think I have enough room to do it here. So this will be e to the power of arc cosine x times cosine of arc cosine x. So the cosine of arc cosine x is x. So x times, so again, cosine of arc cosine x is x. I'm plugging in arc cosine for u, arc cosine of x, and the cosine of arc cosine of x is x. Okay, plus e to the power of arc cosine x times the sine of arc cosine x plus some constant divided by -2. I got a little bunched up at the end there. Hopefully that's lucid. I probably should have used a new sheet, but I'm trying to save the planet. So hopefully you can see that greatness there, the beauty of that integral. This arc cosine is maybe a little undecipherable, and I'm not sure if that made things better, but this is the sine of the arc cosine of x. So there it is again, another great MIT Integration B problem. We'll see you next time.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.